This video is on calculating your enthalpy for your reaction using bond enthalpies. So in order to do this, you're going to have to remember how to draw molecules. So if you need to go back and review that, that is in Chapter 6 notes from last year. So you can find any of those videos or look over any of those notes. And the key to this, or I should say maybe the equation that we need, is that in this case, your delta H of your reaction is going to be the sum of the energy for all of your bonds that are broken minus the sum of the energy for all of the bonds formed. All right, so in doing this, we have to know what bond enthalpy is. That's the enthalpy change for the breaking of a particular bond in 1 mole of a gaseous substance. So it's a gas, it's 1 mole, and it's how much energy is needed to break that bond between those two atoms. So breaking bonds is always endothermic, which means it takes energy to break them. Like you have to put energy in. So that would be positive. And then making bonds is always exothermic. So that would always be negative. And that means when a new bond is formed, energy is released. So another way to look at that reaction that I wrote in, the equation that I wrote in blue is bonds broken is going to be positive and bonds formed is going to be negative. So we're actually saying it's the sum of all of them, but our formed ones are negative. So when you add a negative, that's the same as subtracting. So another way to think about this would be just you're totaling them all up. But you will have to take care of the sign being negative for any of your bonds that are formed. All right, so we look up the amount of energy, this bond enthalpy. We look this up on a table, so this is in your data booklet, and it's an average amount. So it's an average amount to break 1 mole on gaseous molecules under standard conditions. Average refers to the fact that the bond enthalpy is different in different molecules. And therefore, the values quoted the average amount required to break a particular bond in a range of molecules. So they look at a whole bunch of different ones. So like a CO bond you could have in a whole bunch of different molecules. So they kind of average those out. All right. So let's look at this question first. Which one of these processes would be endothermic? And then we'll come back to the data booklet and all that. So I'm going to go through and I'm going to figure out endothermic or exothermic for each of these. So in the first one, endothermic means I'm putting energy in. So think about what's happening in A. I have 2 chlorine atoms, so chlorine plus another chlorine, and they're forming a chlorine-chlorine bond. So we're making a bond. We're forming a bond. And if I go back up here, making a bond is exothermic. So making bond. So this is exothermic. So it's not that one, right? We're looking for endothermic. Okay, look at the next one. I have a sodium atom that's a gas, and it turns into a sodium ion, and an electron is pulled away from that. That's how we get that cation. This is ionization energy. This is using energy is needed to remove an electron. That's ionization energy from last year. And so that is endothermic. Like you have to put the energy in to pull away that electron. So this would be the answer. But let's just go through the rest and double check them. So C, you have a sodium plus a chlorine ion, and together they make a sodium chloride compound. So you have made a bond, right? Sodium's bonding to chlorine here. So just like A, you're making a bond. So this is also exothermic. So it can't be C. And then the last one, you're going from a gas to a solid, nothing else changes. Well, if you're going from a gas to a solid, you have to remove energy. Just like if you were going from a gas to a liquid, like you're taking gaseous water and you want it to be a liquid, or you're taking liquid water and you want it to be a solid. That's maybe something that is something you've seen before. If you want to make water into an ice cube, you have to remove energy. And removing energy is exothermic. So that also would not be D. Endothermic would be the reverse. Anytime you go from a solid to a liquid to a gas, or even skipping the middle, a solid to a gas. All right, so now let's look at this chart. This is what's in the data booklet. This is table 11. And you can see the chart shows what the bond energy would be. This is single bonds. You've got our unit kilojoules per mole. And you just pick the element and you find whatever it's bonding with. So for example, if it was a carbon-chlorine bond, I'd look at carbon, I'd look at chlorine, and this would be the amount of energy it would take. To break it would be positive, to make it would be the same amount but negative. Down below the table, you've got some common double and triple bonds and their energy. All right, so let's go to this example problem. All right, it says use average bond enthalpies to calculate the heat of combustion of methane. So let's write what this reaction would be. So methane is CH4, and combustion means it reacts with O2, and we get carbon dioxide and water. So what we need to do here now is we need to draw these molecules. So CH4 is going to be carbon with 4 hydrogens bonded to it in this tetrahedral shape. Oops, I forgot to balance it. Sorry, guys. CH4, let's see, 1 carbon on each side, 4 hydrogens. So I'd need a 2 here for hydrogen. And then that gives me 4 oxygens on each side. All right, so going back to this. 2O2. So oxygen double bonds to oxygen, and it's got these valence electrons. And I have 2 of these. So 2 sets of those. CO2 would be a carbon in the middle double bonded to an oxygen on each side. And then water is hydrogen bonded to oxygen in this bent shape. And we have 2 of those. Okay, so now what I want to do is I need to sum up the bonds that are broken, the bonds that are formed. We're going to find the energy for them so that we can total it up. So I'm going to make a list. So my reactant bonds are the ones that are going to break. So I'm going to write broken. And I'm going to make a list of what their enthalpies are. Okay, and then for my products, these are the ones that are formed. So I'm going to make a similar little table here. Okay, so what bonds are we breaking on the reactant side? Well, we're breaking all of these CH bonds. So CH, and there are 4 of them. So I'm going to look up the delta H for CH. So CH would be this 414. So it's going to be 4 times 414 because I've got 4 of them. Okay. Then let's see, what else do I have? Oh, I'm breaking an O to O double bond. There's 2 of those. So if I go back to the table and I look at the bottom of it, I've got an O to O double bond right here. So 498. So 2 times 498. All right, so that's going to be my total broken. So these would all be positive, endothermic. All right, so how about on the formed side? I can total this up actually right now. If I do the math here, I get 2,652. All right, formed side. Let's see, I'm going to form this C to O double bond twice. So 2 of those. So if I go back here and I look at the C double bond to O, I've got this right here, 804. So 2 times 804. And then I'm also forming H to O. So I've got 2 in a water, and then I have 2 water molecules. So that's 4 total. So 4 times, if I go back to here, H to O would give me this 463. All right, so if I add all these up, this is 3,460. So now, what is my delta H for my reaction? Well, my delta H for my reaction is going to be broken minus formed. Or you can think of adding them both up, but your formed is negative. So you're adding a negative, which is subtracting. So 2,652 minus 3,460, which gives me negative 808 kilojoules or kilojoules per mole Sometimes the per mole isn't written. But overall, this reaction is exothermic. So it's releasing overall 808 kilojoules per mole of energy. We will do this second one that's listed on there in your notes in class as another example.